talking about using Rust as a language for building developer tooling. In this talk, I'm going to assume that you hear at least a little bit about continuous integration. If you don't, I'm just going to pretend that you do it. First of all, I'll say a little bit about me and how I came to be thinking about this problem in the first place. Sorry. My name is Jeff Parsons. I'm a software engineer. I work for a company called Stile Education. One of my special areas of focus is developer tooling. That is, tooling to help other developers build tooling or other software. That's where the meta comes from. Stile exists to improve scientific literacy throughout the world. Right now, we're trying to do that by building the best science resource around the high school and getting it into as many teachers and students' hands as possible. My personal take on this is that if you want people to make better decisions in life, including what they do at the ballot box, then you need to prepare them with the tools to make sense of all this information that they're getting bombarded with and understand the difference between good information and the self-serving narratives from the likes of oil companies, tobacco companies, and Mark Zuckerberg. We have an enormous library of lessons covering the entire science curriculum for years 7 to 10. That's just a tiny snapshot of some of the units. And a lot of the time when there's something big or interesting happening in the news, or just some news with an interesting scientific angle, we'll publish a science news lesson about it. Sometimes it's something light-hearted, like wombat who comes out in cubes. Other times it's something really serious, like this summer's bushfires and how it relates to climate change. And most recently, we published a lesson explaining the new coronavirus. Being an online resource lets us respond really quickly to changes in the world and changes in the scientific consensus, because we can just get lessons out to tens of thousands of students like that. We also have a flashcard app for skill drilling and some other stuff. So, as you might imagine, there's a decent amount of technology backing all of this. And here it is. This is a screenshot of our build cartoon with a clean build of what we call our big friendly pipeline. I'm sure. The BFP knows how to build everything that lives inside our main monorepo. As you can see in the top right corner here, it took an hour and 50 minutes to build. Everything including the base Docker images all at the start, through to integration tests at the end, and so on. So that's not so bad, but not so fast. That's an hour 50 minutes elapsed, not an hour 50 minutes compute time spent. This screenshot doesn't really paint the full picture. There's actually heaps of interdependencies between all these components up here. Many of them can and do build in parallel. We're using build kites. Does anyone use build kite? Yeah, build kite's awesome, right? We're using their new DAG mode, which lets you give it a graph of stuff to build, and it'll do it for you. So lots is happening in parallel. Here's what that build actually looks like. Bit of a mess, but let's zoom in so we can see some of it. There's a lot going on here, and you can see a lot of it's happening in parallel. So that's actually taking quite a few computer hours, and those computer hours cost dollars. So remember I said this is a graph for our clean build. So that's, sometimes we want to deliberately opt into building everything in case, say, we messed up a dependency or something external has changed, like a website we download some package from has disappeared, or I don't know, the time changed and we've got an assertion that says explode if it's after March. This stuff, we've actually had a test that had that in it. However, most of the time when we're pushing the CI, we don't want to do this. We want to build the smallest set of stuff possible. So we do that. That brings me to the one big requirement for everything else in this talk, which is whenever anybody pushes a commit to CI, we want to build and test the exact set of components that could be affected by that change. So that's to say, no more than we need to, and no less than we need to. So we build too much, we're wasting money. If we build too little, we're not actually testing their commit. That sounds easy enough. We've clearly got some dependencies set up between our components because we had that big graph in build guide. So surely we can use them to whittle down the set of components to what actually changed in the commit, right? Reasonable? Well, not so fast. Again, it's an easy question to ask, but it's not actually all that straightforward to answer. To understand this, let's take a look at a vastly simplified version of the components that go into styles and app stack. In the simplified version, we only have two actual components to build. There's our web client and our backend monolith. Each of these components has its own set of unit tests at the bottom, and then there's a separate set of tests that brings them together and tests the whole system through a browser. At the end, there's a manifest that just describes what we're going to ship. That's just to make it symmetrical and pretty. So let's change some code and examine the implications of that change. This is a contrived commit that changes the version of some package we're using in our web client. Because the previous version we were on got yanked from NPM and now it won't build anymore. Hypothetical. It affects the web client quite clearly because it's in the web client, and anything downstream of the web client. So that is to say, anything that the web client flows into. Doesn't change anything in the back end, so we don't need to build the back end or unit test it. This seems pretty straightforward to me. If it doesn't seem straightforward to you, please yell out now, because nothing else in this talk will make any sense at all. Oh, good. Okay, so say this fix gets merged into master, and there's 5 other developers that have their own branches that are currently being annoyed because their branches are broken by the same bug. So they're going to merge master into their respective branches to get the fix. Now, they've then made these commits on their branches. What should we run now for them? Okay, so these pink commits are on branches that already have web client changes. So clearly for them, we need to build and test the combination of those various web client changes with the new version of left pad that we just got from master. There's nothing new really going on there, you just build and test the web client. That's what we wrote before. What about these blue commits? They're on branches that didn't have any web client changes before. They just had backend changes from before we merged master into them. So what should we build and test now on those branches? Any ideas?
The backend test.
Just the backend test?
And build the backend.
Okay. So let's pick one and have a close look at it. I'm going to assume that we've already built and tested the backend changes that were on the branch before we merged master into it. So we definitely don't need to rebuild the backend because that's been built in for a previous commit. And we definitely don't need to build the backend unit tests because the only reason we need to do them is if the backend's changed. So far so good. But what about the web client and its unit tests? So this branch didn't make any of its own web client changes. It only has changes that were pulled in and built from master. So nothing in the web client we should need to run ourselves. We didn't have our own, and the only web client changes that there are in this branch are actually being built and tested somewhere else. So I think we don't actually need to do that. If we do, I don't know how to prove it. So it makes sense intuitively, but I'm starting to get nervous because it's not clear to me how you actually formalize any of this. After all, it's a different commit we're looking at. It's got a bunch of backend changes mixed with web client changes. But let's just plow ahead and hope this all works out. Okay, if we're not going to build any of those things, then it looks like we don't need to build the browser-based integration test either, because nothing upstream of it's changed. So, okay. I feel like we should have to run the browser-based integration test anyway, though, because we've never tested that version of the web client with that version of the backend. So something in this model of the world is not actually working out right. Let's revisit our original goal. We want to build and test the exact set of things required to demonstrate the correctness of a change. Well, it turns out that if we focus too hard on this notion of a change, we end up backing ourselves into a corner. A change is not actually a very meaningful concept. If we take it literally, then we end up building way too much all the time, because there's all sorts of changes happening in parallel, but they're often equivalent changes to each other, and it's really hard to prove that. So we don't want to do that. Is there a more meaningful concept that we can look at? Turns out there is. It's the concept of the entire content of the tree at any given commit, not what changed. So even though what changed is intuitively what we're thinking about when you look at a commit or a pull request, it's surprisingly irrelevant. This might either be confusing or extremely obvious depending on your perspective. One thing that might help remembering in all this is how Git actually works internally, which is not on changes. Git works with snapshots of the entire tree. The changes come about when you ask to look at what's happened between two commits, and then it synthesizes it for you. So a lot of other tools in this space are actually looking at entire snapshots of the tree as well. These changes are just a convenient concept derived after the fact because we often have questions about it. So this doesn't really help much yet, but let's see what happens if we start thinking about snapshots. We're back at our graph of components. Web client, backend, bunch of tests, and we'll look at the first commit again. Don't worry if you don't remember the details, it doesn't actually matter. Updates left pad, and here's where things diverge pretty quickly. In this new model, we're going to remember everything we've ever built. We're going to store it in the database. And we're going to index it in some way to be determined that lets us check really quickly whether we've previously built a thing before. Also, to be determined-ish. What we'd like is to be able to tell if we already built something where all the inputs to it are equivalent. So, what do I need to build for this commit? Everything. We've never built anything before. We just rolled out this hypothetical fancy new system. So that's pretty straightforward. This commit will be the second we've built in all time. And this time, we're only changing the backend. This is just static. So what are we going to build?
Build the backend.
Build the backend? Yeah, right? Intuitively, we need to build the backend and anything downstream of the backend because it relies on it. But how do we know that? What can we compute to make sure when we're faced with this blue commit that we can then look up in our database and see, oh, we don't need to do this work anymore?
Tree shard.
Ooh, who said that? Excellent. That's a really good start. So, tree shard, the hash of all the code that went into the backend. Because if that changes, it means that our backend will produce a different binary. So we're going to start with the tree shard, sure. Okay. So we hash the backend directory, and we look it up, and we find that we already built it, and so we don't need to do this again. Because there's an entry in our database that says backend with this tree shard. Oh, it's been done. It made this Docker image or whatever. So we're not going to do it. We're going to reuse the work. Another way we could do this is just store all the files in that column, but that would be kind of silly because in practice, the chance for collision, if you just hash it all, is vanishingly small. We don't need to think about it. So now we've got something concrete we can check rather than relying on our intuition. We computed the hash of the backend directory, we look it up in our builds table, and there's no changes. But if there are changes here, we won't find the build in the table, and so we know we have to do it ourselves. What if we ask the same thing for the web client? Because the files are all the same as last time, we will find the build in our table, and we'll know that we don't have to build it again. Okay, these were simple. What about these jobs? These jobs have some files as input. Those are defining the tests to run. But they also use artifacts that came out of those jobs on the left, so the Docker containers we built for web client and backend. Previously, we were using a hash of all the files as a summary of everything that went through the job, but it doesn't sound like that's enough. So what if we just extend that to capture everything else as well? We can hash a whole tree of files. Why not chuck some other stuff into the hash? So let's say we're trying to decide whether to do the browser-based integration tests. It depends on three things: the files that define the tests, everything that went to the web client, and everything that went to the backend. So what do we need to run? Let's find out. Build up our hash in an order that's convenient for this files of the browser tests themselves. They haven't changed, same as before. Contribute the overall job hash from the web client. That's the same too, so still the same. And finally, we contribute this overall job hash from the back end, which we saw before did change. So that means our overall hash is different to anything that's ever happened before, which means we do need to do the browser-based integration tests. All that really tells us is something that seemed kind of intuitively clear before, but we didn't have any way to prove it. And now we do. So we need to run integration tests. Okay. We know what we want to achieve. We have a bunch of jobs that are already running happily on CI. We just want to run fewer of them because they're expensive. We know how we're going to decide what to build and when. So we either need to make something that encapsulates this logic or find some tool that already exists on some shelf somewhere that already knows how to do this. We looked at a bunch of different build tools, considered what we get out of using them and the cost of adopting them versus building our own thing. We had a few considerations going in that were pretty major. First up is building and maintaining our own build tooling is not our core business. So all else being equal, we prefer not to do it, even though it's kind of fun. The second is that we're really happy with build kite. It does a lot for us. We really like its flexible pipelines. We like its bring your own agent model. It's got really nice GUI and its job scheduler. They basically work pretty well. So any solution that couldn't be made to fit in with build kite's model of the world, it'd have to do a lot. Like it'd have to somehow help us replace all these other things as well. The third is that a lot of these tools that are out there, I'm going to pick on Bazel in particular, not because I dislike it, I actually really, really like it. They're very opinionated and they expect to run the show. So we've got a lot of different languages in our stack. We've got all sorts of weird shit that we're pulled in from other vendors. We'd have to do a lot of work to reshape this stuff to fit into the worldview of a build tool like Bazel. Can't write that work off. We've also got a lot of weird cases where we would need to build customizations to Bazel or insert equivalent smart build tool here. So that would have been a huge amount of serious work. And finally, the build system we've got already works pretty well. Disruption sucks. Having to teach people new tools sucks. If you can somehow swap something out that people don't have to even know about most of the time, that's a really nice thing to have. So we decided that it'd be seriously worth considering building something. But we needed to have a same path to get there. The most obvious requirement is that it has to be very, very fast. It's going to be crunching a bunch of hashes. We really like Ruby. We use it for our backend, but doing something that is doing a lot of computation and you want it to happen like that, Ruby wasn't going to be a good fit for that. The second goal we had was around correctness. We didn't want the whole thing to crash out simply because of like a mundane typo in some logging code that happens in an edge case. You don't want to be holding up developers when they're just trying to get their job done. Ideally, you want the tool to be just, it has to work every time. Don't get me wrong, we did write tests for this thing. It's just we prefer to spend the time writing tests for the interesting logic rather than things that could be done with a fact checker. And thirdly, we wanted to be able to focus on building one specific thing that this tool is supposed to do rather than a bunch of boilerplate or glue code. So we wanted to make sure that whatever language we chose or framework we chose, we had access to a bunch of high quality libraries that were related to the stuff that we're trying to achieve with it. And the other thing is, a couple of people in my team, myself included, had previously had very positive experiences with Rust on vaguely similar projects, so we thought that it would be a pretty good idea. We could have gone with Golang for similar reasons, to be honest. There's a bunch of ops tooling out there that's written in Golang, a very strong community around it, and for many of the same reasons that people choose that, pretty close. I think the main reason we went with Rust in the end was it's got a richer type system, and we'd want that for a bunch of other stuff we're thinking of building. So there's a hidden kind of motivation in here as well. We could have gone with Golang. All right, so we decided we're going to build a thing. We ended up choosing Rust because of all those reasons that Rust satisfies very well. By the way, we decided to call the tool Armchair General because it has strong opinions on how things should be done and who should do them, but it doesn't actually know how to do them itself. That's the minor mystery of that one. So let's have a look at the high-level structure of the project, and then I'll run through a bunch of tools we used in building it that you might want if you're doing something similar. So, as you can see in this super elaborate architecture diagram, there's a main...
It's the best one I've seen.
Thank you.
It's so simple.
There's a core Armchair General library that encapsulates all the planning logic and knows how to load the definitions of our components that we're going to build, understands all their relationships. It also knows how to talk to databases and look up whether things have been done yet. And then there's two separate command line tools. There's the main one that knows deeply about our use of build type. So that's the command line tool for that. And then there's a separate tool that is used for building things locally on your dev environment. So that will try to pull stuff from CI if it's already been built, or build it locally. So it's kind of got its own little job scheduler inside it. It's shown in grey because it's not really done yet. It works, but for weird reasons related to the rest of our stack, it's not actually being used yet. Right, here's cool stuff you should know about. For starters, both these binaries are command line tools, so we're going to want command line argument parsers. There's two traits you should know about here: clap, command line argument parser, and struct-opt. I very rarely use clap, even though I love it, because it's a bit verbose, and for most purposes, as long as you're happy with a little bit of macro magic, struct-opt wraps it up in a way that lets you write code like that, where you just say, here are my command line arguments, and will generate help messages, subcommands, nice error handling, parsing for any kind of type you can imagine, because traits are amazing. There's also an ongoing project to roll struct-opt into clap itself, but they're kind of dragging their heels on that one a little bit, so you can't forget that struct-opt exists quite yet. Next is we want to handle a bunch of structured input and output. Things like definitions of components to build, queries, and the build plans that this thing spits out, for example, to send to build card. Armchair General deals mostly with JSON, but also a little bit with YAML. I don't know how widely this is known, but YAML is actually a superset of JSON, so you can use it as fancy JSON with comments, that sort of thing, which we do. This is where SERDI comes in, and yes, that is how it's supposed to be pronounced apparently, along with all its companion crates for specific formats. SERDI, like clap, is incredibly flexible. It also has the same defaults out of the box. All you usually need to do in practice is slap a derive for deserialize and or serialize, depending on what directions you want to go. You want to dump stuff onto the wire or into a file, put serialize. If you're trying to get it the other way, put deserialize. And SERDI takes care of the rest. You can call a function on your giant tree of objects, and you've got JSON, or you've got YAML, or you've got RON, or you've got TOML, or whatever the other one is you use. And incidentally, SERDI is one of the things that made me fall in love with Rust in the first place, because it made me realize how powerful its combination of like core programming language features were. Error handling. Anyone who's been using know that there's been a little bit of a lumpy journey with error handling. The core library has deprecated 2 of the functions on the error trait and replaced them with other stuff. There's been a detour via the failure crate, which produced incredibly valuable experience in the community, which also then led to improvements in the standard library. These are the new kids on the block, and you should definitely throw away whatever you're doing before and adopt these, because we finally got it right. This error on the left just does helpers for building your structured error handling, for example, in a library or somewhere where you really care about your interfaces. Unlike failure, it doesn't show up in your public interface or anything, so no one else has to care that you're using it, but it does amazing stuff for you, like making sure that back traces work, making sure that you can like turn specific other errors into your error if you want to wrap them up but allow people to destructure it later. I'm sure it's got some other cool stuff that I'm forgetting now. But yeah, that's how you want to make your own error types. On the other side is if you want something either quick and dirty or even for the long haul for your applications, there's anyhow, which is meant to be interpreted as like, anyhow. That's effectively a fancy boxed error trait that also makes sure that things like downcasting are actually going to work. It's also got helpers for wrapping up extra context around errors if they came from a particular part of your program so that you can debug things later. And it's got a helper for making an error out of a string for when you just want to go, the thing broke, make that a real error. And one thing to think about with this error, with anyhow in particular, is it's really worth starting with it, even if you're not thinking much about error handling yet. Because then when you come to making some parts of your program have more detailed structured error handling, you might have to make some new error types, but at least your whole program and its functions are in roughly the right shape. So you're returning results and like you're handling them and propagating errors in the right places. It makes it a lot easier when you come to that. So now we're down to stuff that helps me with the core business of this particular tool we're building. A lot of the hard work it does involves trawling through objects in a Git repo and computing hashes. So indispensable things are the Git crate, which is maintained by the core Rust team actually. It basically presents a nice rusty layer on top of the Git 2, which itself is written in C. So it's one of those FFI wrapper crate thingies. Walkdir lets you efficiently crawl directory hierarchies using a visitor pattern. Might sound mundane or easy to do yourself. Please don't. It's really, really slow when you do it that way. It turns out they've done a lot of work to make that sort of thing fast. My initial reaction is, I'll do it myself, but yeah, they've done a lot of work. And Ring provides a bunch of crypto primitives. I'm using it for hashing all the stuff that I find that goes into jobs, like Git object IDs and environment variables and whatever else can affect the outcome of the job. It has to be fast, and Ring is fast. Databases. We're using two. So we use Postgres for all of the shared knowledge that comes from what we built on CI. And then for the developer version of the tool, we have a local store of facts about what you've built, but it also connects to the shared one to find out what it can pull from our Docker registry to avoid building locally. So these are both pretty low level. Postgres, Rustplite is a SQLite, SQLite client. One thing worth knowing about Rustplite is you can actually click on a feature that makes it build its own version of SQLite, so you don't have to worry about like what version's installed on the operating system or shipping that separately or whatever. It'll just compile it statically like it for you. So that makes, if you need some kind of local storage that's more than a single flat file, that's really, really handy. If I was writing any kind of bigger application, you'd also see Diesel on this list. Diesel is like a Swiss Army knife of database stuff for Rust. It's ORM query builder, does all that pretty data access stuff, and supports a bunch of different backends. I've got like 3 queries in this thing, so it was easy to just go for something lower level. This one is heaps of fun. This is an example from Indicatif. I don't know how to pronounce it. I think it's French. And it's a simulation of what Yarn would look like if it was written using this library. The reason I didn't do a GIF of our tool is because I'm bad at making GIFs, but trust me, it looks very similar to this. Cool. If you ever need to show progress from your command line tool, please consider using something like this, because your users are going to love you because they see what's going on. It builds upon another library called Console by the same author, which does things like measuring terminal swapping out emojis for other things if the terminal doesn't support it. So if you want to do fancy stuff in a terminal, but you want it to degrade gracefully, that's a handy one to use as well. And for the sake of completeness, here's the full list of other crates that I'm using for various things. They're not as exciting for the most part, but they're worth knowing about. Log is the de facto standard logging interface in Rust world. There's also a bunch of specific crates like pretty env logger for deciding where you want your logs to go. This just reads environment variables for configuration and then prints pretty colorful messages to the screen. YAML Rust I used as well as Surdy, because it turns out YAML lets you put multiple documents in one file, which is a little bit gross, but also super convenient. And Surdy only ever wants to deal with one top-level object at a time. So I shamefully admit that I use YAML Rust to slice up the file first, and then re-serialize it. Data encoding just
Oh, it's
feels...
going to make it slower.
Yeah, but that's like, that only happens once in the whole program. That's the bit that doesn't matter. I still feel dirty. Data encoding feels a missing, like it's just a gap in the standard library where there's some stuff to do with hexadecimal strings that it doesn't do very well. Itertools is equivalent to two libraries that exist for every language that has iterators, and it's all this like insane things you might want to do with iterators that the language designers thought weren't important enough to include. Including things that are a little bit misleading, like I'm using a sorted method, and I can see why they didn't put this in the standard library, because sorted on an arbitrary iterator, what's that going to do? It's actually going to collect the whole thing into a vector and then sort it and then start feeding you elements again. So you might accidentally use terabytes of memory. Directories tells you where is the socially appropriate place to put your configuration files and databases. I don't know where you're supposed to put them on Windows. This just gives me a path to put stuff in. Chrono, if you're doing anything with times or dates, especially if you're touching time zones, which you better be, don't bother with anything else. Chrono is where it's at. And crossbeam channel is kind of a hangover from when I was using other crossbeam features. I think for what I'm using it for, it's just a faster version of what's in the standard library. So, yeah. That stuff combined meant that I had to write surprisingly little code except for the core planning algorithm, which is about 90 lines. So I've got a bunch of types, a bunch of invocations of other people's code, and then 90 lines of actual interesting logic, which was really satisfying. But there's one other detail of implementation that I think is worth talking about. It's actually a fairly simple testing technique that I started using a few years ago, and then when I found myself using it in writing the tests for Armchair General, I thought I have to share this, even though it's kind of, it seems really simple, but it's really useful. Let's say you've got some list of concepts that might grow or otherwise change. And if it does, there's places in your code that need to be updated to reflect that. To keep it easy, let's pick an example where you've got like some drawing app, and there's all sorts of different widgets you can put onto a canvas. And if you invent a new kind of widget, some parts of your app need to be updated to support that. Or like, I don't know, the bit where you save files or load files or something. It's really easy to write code where someone can just forget about your code, no tests fail, because there's a bunch of tests for all the different widgets, but they didn't even know they had to add one for theirs. Sounds silly, but surprisingly common. I see it all the time in code. So, the fix for this is something I call explode early, explode often. The first step is to make sure that some extremely obvious kind of error, preferably a compilation failure, but maybe a test failure, will happen whenever this set of things, widgets, file types, whatever, changes. That's the explode early. As soon as someone tries to change it, boom, they can't get their code merged because it's broken. The error should ideally tell them where to look in the code to atone for their sins. And hopefully explain why they're being yelled at, why they actually need to do this. It should also tell them what tests they need to update so that they can go and make the other thing that's breaking last bit is really important. The tests that they need to update should be structured so that it's overwhelmingly likely that if they just try and copy and paste their way to freedom, it's not going to work. I've seen a lot of tests where you do have to put something in, but you're not really encouraged to actually test anything, so people don't for some reason. Let's look at a concrete example in Armchair General. This is real code. This is the explode early part. There's logic somewhere that computes the digest of this job struct. That's what we were using to decide whether the work had already been done. I'm not using the inbuilt hash thing that you can derive in Rust because, as far as I'm aware, it's not stable. And I'm also weird and paranoid, so I wanted to be that hash. So if you add a new field, job struct, for example, working tree diff, because you want to work on developers' machines while they're working, then, assuming this is here, all the code branches pass, and yet the job digests aren't taking into account this new, super important bit of information. So, step one is make sure that we're constructing an instance of this struct in a way that forces this to explode if you change the definition of the struct. That's what explode early looks like in this case. It might look different in your case if it's not as simple as adding a field to a struct, but there's usually a way to do it. So that means no constructors, no use of default to make an object and then modify it. You have to spell it out by hand to make sure this explodes. So then they run the tests, and they find an error, and they go, okay, I need to add the field to a struct. And now they end up here, and they can't miss it because there's pumpkins all over this. I actually strongly advocate for writing more issues because they make a difference. The stuff between the pumpkins also explains how to update the test to make everything work again. Okay, so there appear to be a bunch of assertions about doing stuff with particular fields. So I'm in a hurry, I'm just going to copy and paste some assertions and change the setup code to refer to my field. And then we run our test and it still fails. So we're forced to actually go and update the logic. I'll get to why it failed in a second. Instead of just adding stuff to the test file until it passes. If we look back at how the test is written, we'll see why. It's written to count the number of unique digests that it sees. So if you add some references to the field here, but you don't actually update the logic that this is testing, it's going to be off by one. And there's going to be an insertion that says, you added another thing, another test case in the middle of all this, and it had no effect. So we've proved that our test in the middle actually did something. There's all kinds of different ways to apply this concept to make your tests fail by default rather than passing by default. So this pattern is pretty simple. All it really says is that at each step of forcing people to fix the tests and write tests, there should be something that explodes if you do the wrong thing, rather than explodes, or rather than passes if you do the wrong thing. It seems simple, it seems maybe kind of silly, but I've seen so many bugs out of the wild that could have been prevented completely by variations of this. So I encourage you to try and find a way, an excuse to use this somewhere and try it out. Okay, most importantly, did this all work? Yeah, it did. Armchair General is now happily humming away, gathering build plans for our CI server. It's actually saving us a few $1,000s a month in cloud resources that would have otherwise been spent on redundant builds. But I'd say even more important than that, it means people are spending less time waiting for their stuff to build because it's building like 4 things instead of 40 things. In combination with another cool tool we built in-house. Does anyone use Bores? Bores? Yeah. So it's a build queue that combines a bunch of PRs and makes sure they actually work together and then puts them on master. We built a version of Bores that's kind of smarter, but it's deeply enmeshed with all of our stuff. We're hoping to open source it at some point, but it does all sorts of crazy stuff like figuring out probabilities that someone's at fault. So making our builds faster combined with that other tool means that as soon as someone's work has been reviewed in the PR, it's like all basically eating my lunch, as opposed to multiple days previously. And it has been remarkably reliable. We've only had one serious bug the whole thing. Does anyone want to guess where that bug might be?
Pumpkins.
Not the pumpkins.
YAML.
Windows.
Not YAML, not Windows. Syntax. Oh,
Leap year.
Say that.
not SETI.
Funny.
Leap year.
Not leap year. It was in the libgit2 C code that is wrapped up by the git2 crate. So the only serious bug we've come across has been in some C code. And like almost perfectly predictably for my like Rust evangelism, I dug in to find out why that bug existed, and it's because someone forgot to check an error code. What happens is if it's crawling a tree and you're saying walk the directory tree, and it comes across an object that represents a directory, and for some reason it can't read that object on disk, it just goes, move on, it just goes on to the next one. Nearly dumb error. Very smart people wrote that library. And yeah, definitely the kind of bug that Rust would have prevented. Would I do it again? Yeah. Hell yeah. Like if I have another tool that's fairly self-contained, as long as I've looked at the problem domain and satisfied myself that there are crates out there that will support me in doing what I'm trying to do. Like if I'm trying to do stuff with cloud resources, for example, I'll go, oh, is there something for AWS? Oh yeah, there's Risotto. It seems to be really good. Okay, let's do that. As long as I have that experience when I'm planning it, yeah, I would absolutely use Rust for developer tooling or any other little isolated tools that I've built. My experience was that I got it done faster than I would have in another language, and there was a much shorter tail of bugs. The only other bug that I can remember was a performance bug, where some like mission critical memorization, I just like built the thing and then forgotten to hook it up, and only realized, because the rest of it was so fast, this absolutely necessary optimization wasn't actually doing anything. But that's really the extent of it. So yeah, if you want to spend less time debugging stuff, yeah, choose Rust. I've lost a slide. Oh no, I haven't. Okay, cool. So thank you so much everyone for coming along. I enjoy meeting people and talking to them about Rust. It's lots of fun. That's me if you've forgotten. That's my email address. That's my employer I talked about before. And if you're interested in having like a really big impact on the world through helping kids learn about science and understand it, we're hiring. So come and talk to me or Daniel or Peter or Nepa. Yes. Afterwards. Thank you very much.
So before we move on to the next talk, any questions?
Yes, Brendan.
Yes. How did you fare in terms of kind of upskilling the rest of the team on this kind of Rust work?
So we had a big fight.
Yep.
With the people that were likely to be working on this tool.
Yep.
We made a short list of languages based on people's previous experiences and what we believed about them. And then at the end of it, if I recall correctly, we all ended up saying, oh look, I'm happy to use whatever. And so it was the consideration that we might want something with a very rich type system later for other stuff that kind of pushed us down the Rust path more than the Go path. But really to get that set of people on board, all I really needed to do was offer unlimited hours of Rust consulting and coaching, and they seemed pretty okay with it. Yeah, I was nervous about the idea of ramming it down people's throats, and we almost got to that point, but we managed to not quite get there.
Because you never want to do that.
Yeah, like it never gets well. It doesn't matter what tool is the best.
Yeah.
If people don't want it and they're not bought in, it's not.
And do they feel confident in changing the code and working on it, or is it?
That's actually a really good question. I haven't asked recently whether people feel confident, but I have observed that their PRs are flawless.
Cool.
And so they've gotten really, really good at Rust really, really quickly.
Because the issue with developer tooling is you don't want it just to be one person just working on it. You want it to be like the
That would be,
team.
pretty scary, but yeah, no, like from looking at what people are producing and when I sit down and talk to them about it, going through problems, like they picked it up way faster than I expected, which sounds insulting because they're all very clever people. But yeah, it's like worked out pretty well.
That's been my experience too. People pick it up pretty fast. So.
Yeah.
So how long has it been running within the team?
This has only been in production for 2.5 months, 2 months.
People working on it.
Yeah, people made changes. We've actually had another tool written in Rust that was peripheral that we tried first.
Yeah.
So this wasn't technically the first one. It was a tool where, like, say I got hit by a bus. It would have been, well, I hope people would have missed me, but if that tool dropped off the radar and never worked again, it wouldn't have been a big deal. So that was really the first experiment. And then based on that, going kind of well, and other people being able to do bug fixes to that, well, okay, people seem to be okay letting it happen up to. I almost forgot about that. We wrote our own Dependabot. No, it just fills in the gaps that Dependabot doesn't do.
Any other questions?